And so, yeah, so the Cauchy criteria says for all epsilon greater than 0, there exists a natural number, call it H or call it N, such that for all natural numbers, N and M that are greater than H or capital N, whatever you want to call it, the terms satisfy xn minus xm is less than epsilon. So again, the idea is it has some similar things when we talk about things converging, but we don't, again, like I said, we don't need to know what the limit is. And for all, there exists this H value, which is a natural number, call it H, call it N, for all, for all natural numbers M and N greater than that H, the terms satisfy X minus M less than epsilon. And so what that means is that you could have like a sequence and you could have a whole bunch of terms. And so your sequence, could have, I'm just picking some numbers at random, 0.1, 0.05, 0.04, etc. And there's some point, so you pick an epsilon, and there's some number n beyond which all the terms are this close together. And now what this means is you could pick, so it has to be any term beyond this capital N that you pick, or capital H, whichever that you pick. All the terms have to be this close together. That means a term here, call it maybe, XN, and a term a million integers down the road, that difference between that and that has to be less than epsilon. So the criteria seems pretty strict. The fact that you have to find this N or H, sometimes call it, such that any two that you pick, there could be, you'll pick one maybe right here or right here, and even a billion terms away, and that difference still has to be less than epsilon. So it's just kind of a in words, a way to think of what the Cauchy criteria is saying. So let's actually look at some more problems here. Let's see, we take a couple here. And so let's say, let's take this one here. So suppose that you have two Cauchy sequences. So let's do this example here. Show that if, say, xn, xm, excuse me, yn are Cauchy sequences, then the sequence x n yn is a Cauchy sequence. So let's try to think of what we have. Once again, a lot of times what you want to do is maybe do some scratch work to try to figure out, okay, what do we have? What we'd like to show is this is a Cauchy sequence. So we would like to show, that, for given epsilon greater than 0, that this is a Cauchy sequence, which, what does that mean? That's going to mean, say something like, maybe it doesn't matter which order you put this in. I'll maybe do that this minus this, excuse me, xn minus xm, like this, is less than epsilon. So for it to be a Cauchy sequence, we'll have to take this term minus any other term along the way, and that's less than epsilon. And so let's think of what we have to do here. We would have to maybe play with this a little bit. Now, keep in the back of your mind what we know. We know, since this is the Cauchy sequence and this is the Cauchy sequence, and let me put this in a box. We know that xn minus xm is less than epsilon, and ym minus yn is less than epsilon. So we know this because xn, yn are Cauchy sequences. So I'm just going to put this on the side just to keep that in the back of your mind. So what we would like to do is get this thing, somehow use this stuff here that we know, and kind of work it into here. So what we could maybe do is kind of rearrange these a little bit. And if we could put the xn, xm together, so I'm just going to rearrange this just a bit to try to match what we know. Try to put get a different pencil here. Put the xn minus xm together, and put the yn minus ym together, like that. And now one thing that you may have had before, I don't know if I can't remember now if you've had this, is what's called the triangle inequality. I think so. The triangle inequality says that if you have like A plus B, that's always going to be less than or equal to A plus B like itself, the absolute value. So if you have any two numbers or any two expressions in an absolute value, it's less than or equal to the individual absolute values of the individual terms. So we can use that here then. We can say here that we have this and this. Again, keep in mind what we're trying to use here. We want to use this stuff here. This is less than or equal to xn xm plus yn ym, like this. Again, that's from the triangle inequality. And then finally, because we know they're Cauchy, each of those is less than or equal to epsilon plus epsilon. And now we kind of almost pretty much almost have what we want. Though when we do the proof, we would like this to be we would like this just to be epsilon rather than 2 epsilon. But what you can say is epsilon is just a number. So when you're saying that something is Cauchy, you can say that for any epsilon greater than 0, you have a natural number, n or h, whatever you want. And to say beyond that point, all the terms are real close together. Or you can just say for all epsilon divided by 2, you can find an n that such that anything beyond that point. So keep that in mind. So again, so right here you can see what we kind of have here. And when we do the proof, so note if x and y and are Cauchy, there exists an epsilon, excuse me, for all epsilon divided by 2 greater than 0, there exists and n such that for all n m greater than n or h, whatever you want to call it, xn minus xm is less than epsilon over 2, yn minus ym less than epsilon over 2. So, like I said, you can call the ideas, when we say that epsilon, it doesn't have to be epsilon. It could be, you could call it epsilon over 2, some half epsilon, and you're still going to always be able to find an n such that these are two arbitrarily close together. Now, also, if you're kind of wondering, you in case you're thinking, okay, wait a minute, for maybe this sequence, there's going to be a different capital N than this sequence, huh? Because, for example, maybe this sequence here, I'm just going to pick an arbitrary number for a given epsilon over 2. This sequence requires a capital N of, maybe 1,000. And maybe this one requires 2,000, or more. But of course, with this N here is going to be the biggest of those two values. So let's put, so this was the scratch work. So let's put the proof together. So let's take a look at this now. And so proof. So let epsilon be greater than 0. Then, and let's do it this way. And I'm going to do this kind of a little bit more formally. So choose capital N equal to the maximum of, let's say, an x and y, like this. Then for all n m greater than our capital N, we have, and pretty much a lot of this is going just by what our scratch work was. So we want to start with this and then rearrange things a little bit. Yn, ym. Use the triangle inequality. Then this will be less than epsilon over 2. This one's less than epsilon over 2, which equals epsilon, which we want to show. Then, okay, so that's kind of proof. Then down here, we can put some explanation where, so since, and we may put a note. Some people might put it up here in front. It's up to you. Note that since xn, yn are Cauchy sequences, then for all epsilon over 2 greater than 0, there exists an x in the natural numbers, and there exists an y in the natural numbers, such that for all m and n greater than x n, we have that xn minus xm is less than epsilon over 2. And for all m and n greater than ny, we have yn minus ym less than epsilon over 2. So again, sometimes you might want to put this at the very beginning of your proof, or I think maybe it's a little bit easier to put at the end where you're kind of explaining what you're doing up here. So again, the idea is because xn and ym are both Cauchy sequences, then for all epsilon over 2, there's going to be a natural number such that for all m and n greater than that natural number, xn minus xm is less than epsilon over 2. And also there's going to be a natural number ny such that for all m and n greater than y, we have yn minus ym less than epsilon over 2. So that's why when we did our proof up here, we took the largest of these two. That's what this point up here was. We took the maximum of our nx and ny, because we have to take the maximum, because if we take the maximum, then both of these are going to be satisfied, right? Because, when we're picking our capital N here, anything bigger also work. Like say if you're picking, because like here where you're picking your capital N for your Cauchy sequence, any capital N here larger than that will also work, because you can see down here these values have to be anything larger than that. So any larger capital N would work here. Same thing with here, any larger capital Y would also work. So then when we pick the maximum of the two, we're picking the maximum of these two, and that means that it'll work in both cases. See if any of that makes sense. And like I said, it's a matter of what your style is. If you want to somehow put this at the front of your, at the very beginning of your proof up here, some people might prefer to do it that way. That might depend on what would make the most sense to you. See if you have any questions on that. Give you a minute to finish writing everything down and to absorb it. Let me write another one down here. So let's go to this next one here. Show that, once again, show that if X and Y are Cauchy sequences, so is the product of each of the terms. So once again, let's see what we can do with this one here. This one's going to take a little bit more, a little bit more technique here. So again, keep in mind what we have, keep in mind that, we have for all epsilon greater than 0, there exists an N such that, again, I'm not putting all the specifics in the scratch work, such that Xn, and it doesn't really matter which order you do it. Let me, just to kind of emphasize that, let me do it in the other order. Xm minus Xn is less than epsilon. Again, keep in mind, or epsilon over 2, and then Ym minus Yn less than epsilon, or if we need it, epsilon over 2, and then and we almost want to do the same thing as before. So we want to try to get Ym, Yn minus Xn, Yn. We want to get this less than epsilon. And so this time we have to do something a little bit special here. So ym, so start with this. And we're going to have to do is add and subtract something in the middle. So let's say here, see, the problem is we need these terms to be mixed a little bit with x's and m. So let's try, oh, excuse me, let's try something like this. Let's subtract x m y n and add x m y n minus x n y n. And sometimes you may have to play with this a little bit to see, but often when you have these products, you have to add and subtract something. You know, you could maybe try y, then probably yn, ym. Excuse me, if you did xn, ym would probably also work. Just have to rearrange things a little bit. So just so we subtracted this and added this. So we added nothing. So we're allowed to do that. And then we can factor out the xm. Like this. And then we can also factor out the yn over here. Like this. Excuse me, with that ym, excuse me, xn, and like this. So we're getting a little bit closer because see, we have our ym minus yn, xm minus xn. And then let's say here, let's go, once again, let's do our triangle inequality. Put this here, triangle. I'll just put triangle inequality here. And then we can say that this let's see that that's true like that. And let's see if we can say also it's certainly less than or equal. I think it's actually even equal. If we have two, let's see, if we have two factors multiplied together, we can separate the absolute value, can't we? And still say that this is true. Like this. So now we're almost there. The only, in other words, because see, we have bounds for this thing and we have bounds for this thing, but I wonder what we could do with these over here with this xm and yn. You can holler if you think it's something. Yes, sir.
Could say that's less than those replaced with the.
close. Think, let's see, unfortunately, yeah, these we can't, since they're just kind of standalone. These you really can't. Oh, okay.
The other part.
Oh, yes, right. These one here, yes. These can be replaced with epsilon, right? Epsilon over 2. Now, how about this? I probably didn't make it clear. How about this here and this here? What could we, can you think of anything we could say about that? It's not real obvious, but just in case somebody thought of it, it's not real obvious, but what we could say here is that because it's a Cauchy sequence, the sequence converges, and therefore we said a convergent sequence was bounded. So we said that any a Cauchy sequence is a convergent sequence. Convergent sequence are bounded. Then we can say, so let me put this. Sequences are bound. These sequences are bounded. And so this is going to be less than or equal to, say, M. And again, you can call this maybe like an MX for the bound of the X sequence. Plus MY for the bound of the Y sequence. So let me put this down here, bound on the sequence, YN, and this is the bound sequence. I did these in reverse, sorry. This should be on XN, and this was the bounding sequence Y. And so there's some number that's bounding each of those sequences. And once again, if we take the maximum of those two, then finally we could say something like this: M YM minus YN plus M XM XN. And then this time, where M is the maximum of the MX MY. So see if there's any questions so far. If there's anything that doesn't look right or anything so far. And then let's see. So then finally we know, so we could say, let's see what we're getting at here. We can say that this is less than or equal to M epsilon over 2 M epsilon over 2. And that's going to be equal to, so this is going to be 2M over epsilon over 2. Did I do that right? I guess that's right. Equals epsilon E. So let's see how we could fit that in. So what would, let me think, what would we have to set? So we're going to have to reset our bounds a little bit, so do the bounds on each of these sequences, we're probably gonna have to adjust them a little bit. So we can say, let's see, I'm trying to think of a nice clean way to write that. We could, yeah, I think this would work okay. So let's take a look. We could maybe say something like this. Okay, that's kind of the scratch work. So now let's go through and see if we can set up the proof. And maybe we'll do this ahead of time this time. So let's say, start with, since xn, yn are Cauchy sequences, they are bounded by some numbers mx and y respectively, and set m to be the maximum of those two. And also, and once again, let me just think of how we want to say this. Also, yeah, for all epsilon over 2 greater than 0, and you could even try to think of, you could maybe even put it in here, maybe epsilon over 2m. Let's say that for all epsilon over 2m greater than 0, there exists an nx in the naturals. And let me do this one at a time this time, such that for all n m greater than nx, we have xm minus xn less than, and we can put our bound in here, less than 2m, like this. And for all, yeah, right, yeah, we have that, that's true. For all epsilon over 2m, excuse me, 2m greater than 0, there exists an ny in n such that for all, let me just use a symbol again, sorry, that for all n m greater than ny, we have ym minus yn less than epsilon over 2m. So once again, this is, I'm putting the preliminary stuff first this time. So once again, epsilon is an arbitrary number, so you can say for epsilon or for epsilon divided by 2m in each case, because they're Cauchy sequences, we have that these are true. And so now, and again, if you wanted to just be sure, when you do this max here, you could include 1 just to make it a little bit cleaner so that you wouldn't have a real small number for m. And that would kind of, and it's going to work whether you have like your bound is going to be a small number, a large number, but if it's 1, you can, if you take it as a max of 1, then you can say, it could be this could be the max, this could be the max, but if these are both less than 1, then you could also put a comma 1 here, make that to be 1 if it's less than 1. So that would be real clear to everybody that when you're saying this step right here, the m is actually going to make this smaller. But let's go through now. Let me just go through and then. So that's kind of the preliminary stuff. And then so let epsilon be greater than 0. And then we're gonna choose n to be the maximum of nx, ny, and then for all n and m greater than that m, that n, we have, and let me go through this pretty much through the same steps that we did before. We have that x m y m minus x n y m is equal to x m. Excuse me. This one here should be n. Sorry, and then that's going to be I know I'm going to mess up these subscripts here. So we did the x m y n plus x m y n. At this point, we're kind of repeating a lot of our scratch work. X n y n, and then we're just going to factor out what we had here. X m y m y n plus, and then over here we factored out this one, x m x n, like this. And then we use a triangle inequality and said that this and then we picked, remember, we already defined our capital M as the maximum of both of the sequences. So this is going to be less than or equal to M. And then I had to put that absolute value here, Y M Y N plus M X M X N. And then we said that because these are Cauchy sequences, we said that this over here is less than epsilon over 2m m epsilon over 2m. And I realized now once I made the comment about being 1, it really was not necessary. We don't need to have a 1 in there. So this is going to be 2. So the m's will cancel. So we have 2 epsilon over 2 equal epsilon. So the idea is we started with this and showed that was less than this. So xm, ym, xn, yn is less than epsilon. So see if there's any questions or anything that doesn't make sense in that. If you have any questions at all. Does this make you really glad you took this course? So not everything. Now maybe that makes a lot of sense to you. Probably, I'm guessing the first time you've seen this looks pretty crazy. But like, when you go, if you go more in advanced stuff, you kind of just get used to kind of doing these sort of things over and over. It definitely, for everybody, it seems strange at first, but just like anything else, you get used to it. So let me do a couple more here, or maybe just one more real quickly. This one isn't quite as bad. So let me do this one here. And let's do this one right here. And so let's define the sequence, and n xn is the square root of n. And note that the limit as n goes to infinity of xn plus 1 minus xn is 0. But the sequence is not Cauchy. And so it's kind of interesting when you think about this, because as you're taking square roots, as your numbers get bigger, you can take 2 consecutive square roots, and these numbers are actually getting closer and closer together. Now we could prove it formally, but we can even just do what you might have done like in calculus 2. So this is just it doesn't ask us to do this, but note that if you do the limit of x approaching infinity of xn plus 1 minus xn, what is that going to mean? That's going to mean as n approaches infinity, that's going to be like, say, the square root of n plus 1 minus the square root of n. And you remember from calculus, you would do like the conjugate when you did these. And remember, you multiplied by like the conjugate, which was n plus 1 plus square root of n, square root of n plus 1, square root of n like this. And then when you remember, when you multiply the top out, and to run out of time, I won't do all the steps. Remember, when you multiply the top out, you'll end up with, and you can try this at home to verify it, is that you'll end up with n plus 1 minus n. And then the denominator, n plus 1 plus square root of n, like this. And so you end up with 1 square root of n plus 1 square root of n, like this. And that obviously, we could go ahead and prove that, but obviously that's going to go to 0 because the denominator is going to just blow up forever and ever. So that's going to obviously go to 0. And we weren't asked to prove it. We just said that note that this is true. So the limit, these two are getting closer and closer together, but they're not Cauchy. So let's show it's not Cauchy. And let me do it real quickly. So if we do xm minus xn is going to be xn minus n. And then you can just choose. Remember, the idea is you can choose any two values beyond any number that are far apart. And so like when I did this, choose, let's say that m is 16n, like this. No matter what the n is, you'll just take your m for 16n, and this will be like this. And this is going to be 4 square root of n minus n equal 3 square root of n. And obviously that's going to be greater than 1 always. So it's not Cauchy. That's kind of an informal way to show it's not Cauchy. But the idea is no matter what capital N you pick, you can pick one n and pick your m to be 16m. And there are a lot of other choices you could have picked here. You didn't have to choose that one. Pick anything. And then these are always going to be separated by 3 square root of n, and n is going to be a big number. So that's going to be greater than 1. So that's going to be, so if your epsilon is anything less than 1, you can show it's not Cauchy. And we're out of time. Any questions on anything like that? Okay, good.